Good morning. Today I am going to discuss NEET, CET and JEE questions on the topic moving charges and magnetism and matter. First one, a cathode ray beam is bent in a circle of radius 2 centimeter by a magnetic induction 4.5 into 10 to the power minus 3 Weber per meter square. The velocity of electron is. In this question, cathode ray beam is entering the field normally. So, it moves in a circular path of radius r, which is given by the formula r equal to m into v divided by q into b. You have to calculate velocity of the electron. So, modify the formula v equal to q into b into r divided by m, where q is charge, it is the electron 1.6 into 10 to the power minus 19, magnetic field is given 4.5 into 10 to the power minus 3, radius of the path is 2 centimeter, 2 into 10 to the power minus 2, its electron mass is 9.1 into 10 to the power minus 31. Simplify that, which comes equal to 1.58 into 10 to the power 7 meter per second. So, the answer is D. Second, a proton, deuteron and an alpha particle enter a magnetic field perpendicular to the field with the same velocity. What is the ratio of the radii of circular paths? Here, 3 charged particles enter the field normally. So, they move in the circular path of radius r equal to m into v divided by q into b. All the 3 enter the same magnetic field b and with the same velocity. So, v constant, b constant implies r proportional to m by q. Therefore, radius of proton is to radius of deuteron is to alpha is mp by qp is to md by qd is to m alpha by q alpha. Write it in terms of proton mp by qp. Mass of deuteron is 2 times the proton, charge is equal to proton. Alpha particle mass is 4 times the proton, charge is 2 times the proton, which gives rise to 1 is to 2 is to 2. So, the answer should be A. The current sensitivity of moving coil galvanometer depends on current sensitivity SI is given by N into B into K, B into A divided by K. So, it depends on number of turns in the coil, magnetic field, area of the coil and couple per unit twist. So, the answer is depends on number of turns in the coil. So, A is the answer. In cyclotron, the resonance condition is. So, in case of cyclotron, you have to adjust the frequency of the applied AC such that charged particle should move in the circular path within the disc. That is possible only when frequency of applied AC equal to frequency of revolution of the charged particle. So, the answer is A. Fifth one, a moving coil galvanometer has a resistance of 900 ohm. In order to send only 10% of the main current through this galvanometer, the resistance of the required shunt is. So, this is related to conversion of galvanometer into ammeter. To convert galvanometer into ammeter, resistance, that is shunt required equal to Ig into G divided by I minus Ig, where Ig is current required for full scale deflection of the galvanometer. Here it is only 10% of the main current, 10% is 10 by 100, which is equal to 0.1 I into galvanometer resistance is 900 ohm, current I minus Ig is 0.1 I, which gives rise to 0.1 into 900 I divided by 0.9 I. 0.1 by 0.9 is 1 by 9. 900 by 9 is nothing but 100. So, the answer is 100 ohm. So, B is the answer. A portion of a conducting wire is bent in the form of a semicircle of radius r as shown below in the figure. At the center of the semicircle, the magnetic induction will be. Here, as shown in the diagram, a semicircle is given, O is the center, current I is flowing through this. Thus, this consists of three parts: straight portion and the arc. For these two straight portions, point is on the axis, they will not produce any magnetic field. So, magnetic field is only due to the arc. For that, field at the center of arc is given by the formula mu naught I divided by 2r into theta divided by 2 pi, where theta is angle subtended by the arc at its center. In this case, angle subtended equal to 180 degree, which is pi radian. Therefore, it should be mu naught I by 2r into pi divided by 2 pi, which is mu naught into pi I divided by 4 pi r. So, unit is Tesla. Answer should be D. A helium nucleus makes a full rotation in circle of radius 0.8 meter in 2 seconds. The value of the magnetic field induction in Tesla at the center of circle will be. Here, helium nucleus is making a full rotation equivalent to a current carrying loop. You have to find out field at the center, which is given by mu naught I divided by 2r. Mu naught by 2r into current is not given, charge flowing is given, so it can be written as q by t. So, mu naught by 2r into charge in case of helium nucleus is 2e divided by t. Answer is given in terms of mu naught, retain mu naught, 2 cancels, E equal to 1.6 into 10 to the power minus 19, R equal to 0.8, time taken equal to 2 seconds. 0.8 into 2 goes with 1.6. So, the answer is 10 to the power minus 19 mu naught. So, C is the answer. The distance between two magnetic poles is doubled and the pole strength of each is made half. How will the force between them change? So, two magnetic poles attract or repel based on the polarity of the poles. Force between the two can be written by mu naught by 4 pi into product of pole strength divided by square of the distance between the poles. Therefore, F dash equal to mu naught by 4 pi into pole strength is made half. So, Qm by 2 into Qm by 2. Distance between them is doubled. So, it is 2r square, which is equal to 2 into 2 4, 2 square 4, 4 into 4 16, numerator is nothing but F. So, F dash is 1 by 16th the original. So, the answer is D. A straight wire carrying current I is turned into a circular loop. If the magnitude of magnetic moment associated with it in MKS unit is M, the length of wire will. Straight wire carrying current I whose length L is converted into a circular loop of radius r. You have to write length of the wire in terms of magnetic moment. Magnetic moment is nothing but current into area of the loop, which is I into area of the circular loop is pi r square. But circumference of the loop is nothing but length of the wire implies R equal to L by 2 pi. So, it is equal to I into pi into R can be replaced by L by 2 pi square, which is I into L square by 4. Pi by pi square is pi, which is equal to m, implies L square is 4 pi m divided by I, or L equal to square root of 4 pi m divided by I. So, the answer is B. A magnetic needle is lying in equilibrium in a uniform magnetic field B. To rotate it through 60 degree, we need to spend energy W. How much torque needs to be applied to keep it in that position? So, initially it is in equilibrium, when not mentioned it is a stable equilibrium, for that angle theta is 0 degree, should be rotated to 60 degree. So, theta 1 equal to 0 degree, theta 2 equal to 60 degree. Work required equal to W. Now, how much torque needs to be applied to keep it in that position means when angle equal to 60 degree, that is tau equal to m into b into sin theta, which is m into b into sin theta 60 degree. But answer is given in W, use this formula. W is mb into cos theta 1 minus cos theta 2, which is mb into cos 0 degree minus cos 60 degree, cos 0 1, cos 60, 1 divided by 2, 1 minus 1 by 2 is 1 by 2, which is mb by 2 equal to W, implies mb equal to 2W. Therefore, this is 2W into sin 60 is root 3 by 2, which is root 3 times W. So, the answer should be C, root 3W. Relation between vertical component ZE and horizontal component HE at a place where dip angle is 60 degree is. If you consider the magnetic meridian, this is the orientation of the needle means, which indicates total field of earth. With the horizontal, it makes an angle of I, which is called dip. This is nothing but horizontal component HE, this is vertical component ZE. Therefore, tan I equal to ZE divided by HE, implies ZE by HE equal to tan I, where I is 60 degree, tan 60 degree, tan 60 degree equal to root 3, implies ZE equal to root 3 times HE. So, the answer should be Z equal to root 3 HE B. The magnetic susceptibility of a material of rod is 499. Permeability of vacuum is 4 pi into 10 to the power minus 7 Henry per meter. Absolute permeability of the material of rod in Henry per meter is. Here you have to calculate absolute permeability of the material of rod. A formula for relative permeability mu r, which is 1 plus chi. Mu r can be written as mu by mu naught, which is 1 plus chi. Therefore, mu equal to mu naught into 1 plus chi. Mu naught is 4 pi into 10 to the power minus 7, 1 plus chi is given susceptibility 499, which is 4 pi into 10 to the power minus 7 into 500. 500 into 2000, 4 is nothing but 2000. So, 2 pi into 10 to the power minus 4. So, the answer is B. The variation of the intensity of magnetization with respect to the magnetizing field in a diamagnetic substance is described by the graph. So, whenever diamagnetic material is placed in the magnetic field, it gets magnetized, but it is magnetized weakly, and magnetic field attained is opposite to the applied field. So, refer the graph. OA, OB field in the direction of the applied, OC, OD field opposite to the direction of the field, where increasing the smaller order is OC. So, it is indicated by graph OC. So, the answer is A. A long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns per centimeter is made of, the new value of magnetic field is. Whenever current is flowing through a solenoid, field at the center is given by the formula mu naught N into I. N number of turns per unit length, I is the current. So, new magnetic field is mu naught into number of turns per unit length is made of N by 2. Current is doubled 2I, which gives rise to mu naught Ni is equal to original. So, the answer should be C. A current of 3 ampere is flowing in a linear conductor having a length of 40 centimeter. The conductor is placed in a magnetic field of strength 500 Gauss and makes an angle of 30 degree with the direction of the field. It experiences a force of magnitude. There is a conductor carrying current I, which is placed in a magnetic field B, making an angle theta. Theta is given, which is equal to 30 degree. You have to find out force acting on that, which is given by the formula F equal to BIL into sin theta. Magnetic field is given 500 Gauss, convert it into Tesla, 500 into 10 to the power minus 4. Current is given 3 ampere, length is given 40 centimeter, which is 4 into 10 to the power minus 40 into 10 to the power minus 2, which is 4 into 10 to the power minus 1 into theta sin 30 degree. Sin 30 is 1 divided by 2. 4 by 2 is 2. 2 into 3, 15. 15 into 500. So, it becomes 5 into 10 to the power 2 minus 4, 10 to the power minus 2, minus 2 minus 1, 10 to the power minus 3 into 4 into 3, 12. 12 into 1 by 2, 6. 5 into 6, 30 into 10 to the power minus 3, which is equal to 3 into 10 to the power minus 2 Newton. So, the answer should be B. A proton and an alpha particle enter a uniform magnetic field perpendicularly with the same speed. If proton takes 25 microseconds to make 5 revolutions, then the time period for the alpha particle would be. So, a proton and alpha particle are moving in the same magnetic field, they are moving perpendicularly with the same speed, implies they should move in the circular path. Time period of alpha particle is required, time period is given by 2 pi m divided by q into b. Proton and alpha particle move in the same field, so B constant, mass is different, charge is different. Therefore, time period of alpha by time period of proton is mass of alpha by mass of proton into charge of proton by charge of alpha. Since B constant, 2 pi constant, T proportional to m by q. Mass of alpha is 4 times proton, charge of alpha is 2 times the proton, which gives rise to 2. So, T alpha is 2 times the period of proton. Period is nothing but total time taken by total revolution, which is 25 micro divided by 5 revolution. 25 by 5 is 5, 5 into 2, 10. So, the answer should be 10 microsecond C. A square coil of side A carries a current I. The magnetic field at the center of coil is. Square coil is given. This is the square coil. Side equal to A. Here current flows in this direction. Here it is this direction. Current I is flowing. Find out field at the center. You can split the square coil into 4 straight conductors. They are at equal distance from O. Should produce the same magnetic field. Now check the direction of the field. Field due to this arm is inward. Field due to this arm is also inward according to right hand clasp rule. Field due to this arm is outward. Field due to this arm is also outward. So, 2 fields are inward, 2 fields are outward, but all of them are equal implies these 2 cancel these 2 fields. Therefore, net field at the center is 0. So, the answer is A. 2 thin long parallel wires separated by a distance d carry a current of I ampere in the same direction. They will. So, 2 straight conductors are separated by a distance of d, carry current in the same direction, both carry same amount of current. So, force F equal to mu naught by 2 pi into product of the current by distance between them, which is equal to mu naught by 2 pi into I square divided by d. Whenever current directions are same, they attract each other. Whenever current directions are opposite, they repel each other. So, the answer should be they attract with each other with a force per unit length of mu naught I square divided by 2 pi d. So, the answer is B. The orbital speed of electron orbiting around a nucleus in a circular orbit of radius 50 picometer is 2.2 into 10 to the power 6 meter per second. Then the magnetic dipole moment of an electron is. Here electron is revolving around the nucleus in a circular orbit. So, it possesses dipole moment. Dipole moment of revolving electron, which is given by the formula EVR divided by 2, where E is the charge 1.6 into 10 to the power minus 19, V is the speed, which is 2.2 into 10 to the power 6 into R is the radius, which is 50 pico 10 to the power minus 12 divided by 2. 2 ones are 2 into 1.1. 50 is 5 into 10. So, 10 power 1, 10 power 6, 10 power 7, 7 minus 12 minus 5. Minus 5 minus 19 is minus 24, 10 to the power minus 24. 1.6 into 5, which is equal to 1.6 into 10 is 16, 1.6 into 5 should be 8. So, 8 something in 10 to the power minus 24. So, the answer is C. A deuteron of kinetic energy 50 kilo electron volt is describing a circular orbit of radius 0.5 meter in a plane perpendicular to the magnetic field. The kinetic energy of a proton that describes a circular orbit of radius 0.5 meter in the same plane with the same magnetic field is. Here deuteron and proton are moving in the same magnetic field. Both have radius 0.5 meter, implies R is same. Kinetic energy is equal. Radius of the circular path in terms of kinetic energy, R is mv by qb, m into v is momentum. Momentum can be written as square root of 2m into kinetic energy. So, R is same, proton, deuteron have same charge, Q constant, both are in the same field, B constant, 2 constant, variable is M and Ek. So, M into Ek should be constant, implies so mass of deuteron into kinetic energy of deuteron equal to mass of proton into kinetic energy of proton. Mass of deuteron is double the proton, therefore kinetic energy should be half of a proton. So, mass is double means kinetic energy should be half. Here you have to calculate kinetic energy of proton whose mass is half of deuteron, therefore kinetic energy should be double the deuteron. So, kinetic energy of proton is 2 times the kinetic energy of deuteron, which is 2 into 50 kilo electron volt, which is 100 kilo electron volt. So, the answer is C. An infinite straight conductor carrying current to 2I is split into a loop of radius r as shown in the figure. The magnetic field at the center of the coil is. There is a coil of certain radius here, O is the center. Current 2I enters, which splits into I each. Here it becomes again 2 times I. So, due to circular loop, there is magnetic field at O. Current in the lower arc is in anti-clockwise direction, upper arc is in clockwise direction. So, definitely they produce magnetic field in the opposite direction. Since length equal, current equal, I into length should be constant according to Biot-Savart's law. They produce same amount of magnetic field in the opposite direction, therefore net field is equal to 0. So, the answer is D. A conducting circular loop of radius r carries a constant current I. It is placed in a uniform magnetic field B naught such that B naught is perpendicular to the plane of the loop. The magnetic force acting on the loop is. There is a current carrying loop. This is nothing but plane of the loop. Now, it is placed in a magnetic field such that field is perpendicular to the plane of the loop. So, this is plane of the loop means this should be the direction of magnetic field. Either field is inward or the field should be outward. Now, magnetic field is perpendicular to the plane of the loop. Current I is flowing through the loop. Now, you can split it into large number of small straight conductors. Force acting on them can be found by using Fleming's left hand rule. This indicates the direction of the field, this indicates the direction of the current, this indicates the direction of the force. So, field is inwards, current is to the right, force should be in the upward direction. Here current downwards, force should be outward. So, at every point force is acting in the outward direction, therefore, total force becomes equal to 0. So, the answer is C. 3 wires are situated at the same distance. A current of 1 ampere, 2 ampere, 3 ampere flows through these wires in the same direction. What is the ratio of F1 by F2, where F1 is force on first conductor, F2 is force on second conductor. Here 3 conductors given, first, second, third, separated by equal distances. This is nothing but 2. Carry current 1 ampere, 2 ampere and 3 ampere. You have to calculate F1 divided by F2. F1 is the force on first conductor. First conductor, second conductor carry current in the same direction. So, second conductor attract the first. Third, first current in the same direction, it also attract the first. So, total is sum of the 2. Force is given by constant into product of the current by distance d. So, it is 1 ampere between these two, 1 ampere into 2 ampere, distance d. when you take the ratio, constant cancels out, plus between these two 1 into 3, distance is nothing but 2 times d. For F2, force on the second conductor, first one, second one carry current in the same direction, force should be towards the first. Second and third, same direction, towards the third. Therefore, these two forces are in opposite direction. Therefore, you have to find out the difference, which is product of the current between these two. 1 into 2, distance is d, larger minus smaller. So, this is smaller, plus 2 into 3 divided by distance is d, which becomes 2d common denominator, numerator is here 4, here 3, 4 plus 3 7 by d common denominator, 3 into 2 6 minus 2, 6 minus 2 nothing but 4, which is equal to 7 divided by 8. So, the answer is A. A very long straight wire carries a current I. At the instant when a charge plus q at point P has velocity as shown, the force on the charge is. There is a straight current carrying conductor I. There is a point P where charged particle is moving to the right with a velocity v, which is positively charged particle. This direction is given as Ox, this direction is given as Oy. This charged particle should experience force due to magnetic field produced by the first conductor. Field at the point P can be found by using right hand clasp. So, current in the conductor upward, here field is in inward. So, magnetic field B is inward. Force on the particle can be found by using Fleming's left hand rule. Field direction, current direction is the direction of motion of positive charge. So, field is inward, velocity is direction of motion, current direction, force should be in the upward direction, implies along OY. So, the answer should be A. A uniform electric field and uniform magnetic field are acting along the same direction in a certain region. If an electron is projected in the region such that its velocity is pointed along the direction of fields, then the electron. There is magnetic field B and electric field E, both are in the same direction. In that direction itself, a charged particle is projected with velocity v. Whenever particle moves parallel to the magnetic field, there is no magnetic force. Magnetic force equal to 0, but it experiences electric force. Since a particle is a negatively charged one, should experience force opposite to the direction of electric field, hence its speed goes on decreases. So, the answer should be B, its speed decreases due to electric force. A square loop carrying a steady current I is placed in a horizontal plane near a long straight conductor carrying a steady current I1 at a distance d from the conductor as shown in the figure. The loop will experience. There is a straight conductor carrying current I1. There is a loop carrying current I. Distance, this is nothing but d, this is nothing but side of the given loop. Now, these two sides are at same distance from the straight conductor. So, net force on the loop due to that two is 0. Now, these two are at different distance from the conductor. Here current direction same, implies straight wire should attract this R. Here current directions are opposite, implies straight conductor should repel this R. But force is inversely proportional to the distance. If distance is more, force is less. So, here there is a repulsion, distance is more, so repulsive force is less. Here attraction, distance is less, force is more. So, attractive force is greater than repulsive force, hence net will be attractive force. So, the answer should be net attractive force which is towards the conductor. So, the answer is D. Two similar coils of radius r are lying concentrically with their planes at right angles to each other. The currents flowing in them are I and 2I respectively. The resultant magnetic field induction at the center will be. So, two similar circular coils given. If this is one coil, this is the another coil, because planes of them are perpendicular to each other. Whenever planes are perpendicular, current flowing through a loop produces magnetic field which is perpendicular to its plane. Since the planes are perpendicular, magnetic fields are also perpendicular. So, if one produces B1, another produces B2, they are perpendicular to each other. Therefore, resultant magnetic field should be root of B1 square plus B2 square. Field at the center of loop is given by mu naught into current by 2 times r, here square of the distance, here radius is nothing but capital R. One carry current I, another carry current 2 times I by 2r whole square. Here 1 times the term square, here 2 times the term square, 1 square 1, 2 square is 4, 4 plus 1 is nothing but 5, within the root 5, remaining mu naught I by 2r whole square. If you take it outside the square root, mu naught I divided by 2r. So, the answer should be root 5 mu naught I by 2r. So, A is the answer. Electron move at right angles to a magnetic field of 1.5 into 10 to the power minus 2 Tesla with the speed of 6 into 10 to the power 7 meter per second. If the specific charge of the electron is 1.7 into 10 to the power 11 coulomb per kilogram, radius of circular path will be. Here electron is moving in the field normally, implies should move the circular path of radius m into v divided by q into b. Specific charge is given which is nothing but charge per unit mass. So, I will bring mass to the denominator, v by q by m into b, where v equal to speed which is given as 6 into 10 to the power 7. Charge per unit mass is specific charge which is 1.7 into 10 to the power 11 into magnetic field is 1.5 into 10 to the power minus 2. Simplify that, which comes equal to 2.35 centimeter. So, the answer is D. A charged particle moves through a magnetic field in a direction perpendicular to it, then the. So, charged particle moves perpendicular to the field, implies it should move in the circular path of a certain radius r. It has velocity. If this is the direction of velocity continuously changes. There is acceleration towards the center whose direction also continuously changing. So, since direction of v changes, velocity variable, direction of a changes, a is also variable, direction of the particle is also changing. Since force is acting perpendicular to the velocity, there is no change in the speed of the particle. So, the answer should be B, speed remains unchanged. In the magnetic meridian of certain place, the horizontal component of earth field is 0.26 Gauss and dip angle is 60 degree. The magnetic field of earth at this location is. Horizontal component of earth magnetic field is given, you have to calculate total magnetic field of earth. Horizontal component of earth field is given by the formula BE into cos I, where I is called inclination or dip, BE total field. So, BE equal to HE by cos I. HE is nothing but 0.26 cos, dip is nothing but 60 degree, cos 60 is 1 by 2, which gives rise to 0.52 Gauss. So, the answer is C. Gauss law in magnetism signifies. So, according to Gauss law, total magnetic flux due to magnet is always equal to 0, because magnet always possess north pole and south pole. If it consists of only one pole, then the value should be different from 0. So, what does it signify? There is no magnetic monopole. So, the answer should be B. Magnetic monopole does not exist. Assertion: when small holes are made in the body of the magnet, its magnetic moment decreases. Reason: for a magnet, intensity of magnetization remains constant, and on making holes, magnetized volume decreases, hence magnetic moment decreases. So, whenever there is a magnet, if certain part of the magnet is removed, then definitely this much of volume is reduced, corresponding magnetic dipoles are removed, therefore magnetic moment decreases, but intensity of magnetization remains the same, volume also decreases. So, volume V decreases, magnetic moment decreases, since intensity of magnetization remains the same. So, both assertion and reason are correct. Reason explains assertion, because I constant, as m decreases, volume decreases, m also decreases. So, the answer should be A. Both assertion and reason are true, and reason is the correct explanation of assertion. If a magnet is suspended at an angle 30 degree to the magnetic meridian, the dip needle makes an angle of 60 degree with the horizontal. The true value of dip is, there is a magnetic meridian. Whenever dip is measured in the magnetic meridian, it is called true dip. If it is measured in some other plane, it is called apparent dip. Now, it is measured in some other plane. This plane with the magnetic meridian makes an angle of theta. Then this is nothing but h into E. Component HE along this plane is nothing but HE cos theta, which is equal to HE dash, but both have same vertical component. So, vertical component same, but horizontal components are different. Therefore, tan delta, where delta is true dip, is ZE divided by HE. Tan delta dash is apparent depth, which is ZE, same vertical component, different horizontal component, implies tan delta dash is ZE by HE dash is nothing but HE cos theta. ZE by HE is tan delta divided by cos theta. You have to calculate true dip, nothing but delta. So, tan delta is tan delta dash into cos theta. Tan delta dash is tan 60 degree, angle is nothing but 30 degree, cos 30 degree. Tan 60 is root 3, cos 30 is root 3 by 2, which is equal to 3 by 2, implies delta is tan inverse of 3 by 2. So, the answer is B. When a bar magnet is suspended in an uniform magnetic field, then the torque acting on it will be, two lays are given, you have to find out value of torque based on the angle theta. torque acting is given by mb into sin theta. In least one, it is maximum when theta equal to. For torque to be maximum, sin theta should be maximum. Sin theta maximum value is 1 when theta equal to 90 degree. So, tau is maximum when theta is 90 degree. Therefore, A goes to H. B, half of maximum. Torque should be mb divided by 2, half of maximum when sin theta is 1 by 2. Sin theta is 1 by 2 when theta is 30 degree. So, theta should be 30 degree. Therefore, B goes to G. So, A goes to H, B goes to G. Root 3 by 2 times the maximum when sin theta is root 3 by 2, for it should be 60 degree. So, tau equal to root 3 by 2 times mb when theta equal to 60 degree, because sin 60 equal to root 3 by 2. Therefore, C goes to F. 1 by root 2, tau is mb by root 2, for that sin theta should be 1 by root 2 when theta equal to 45 degree, implies D goes to E. So, the answer should be A goes to H, B goes to G, C goes to F, D goes to E. So, A is the answer. The neutral point in the magnetic field of a horizontally placed bar magnet is a point where magnetic field due to the bar magnet is. A point is said to be neutral point where net magnetic field at the point is 0. There is magnetic field, neutral point in the magnetic field of horizontally placed bar magnet. So, due to the bar magnet there is magnetic field. To neutralize that, earth magnetic field should be opposite to the magnetic field of bar magnet, but it is equal to that of the bar magnet. So, the answer should be its field should be equal to that of earth, but in the opposite direction, hence net field is 0. So, the answer should be D. A bar magnet of magnetic moment 4 ampere meter square is free to rotate about a vertical axis through its center. The magnet is released from rest from east to west position. Kinetic energy of the magnet in north south position will be, B is given 25 micro Tesla. So, bar magnet of magnetic moment is given, it is free to rotate about the vertical axis. Initially it is along east west direction, implies with the magnetic field is along north south direction, it makes an angle of 90 degree, theta 1 is 90 degree. Finally, it should be turned to north south direction where theta becomes equal to 0 degree. So, angle made by the bar magnet with the existing field are initially 90 degree, finally 0 degree. You have to calculate kinetic energy of the magnet when it turns from east west position to north south position. Loss of potential energy is nothing but gain in kinetic energy, which is equal to kinetic energy gained is minus mb cos theta 1 minus of minus mb cos theta 2, which is equal to minus mb cos 90 plus mb cos 0 degree. This is 0 cos 0 1 m into b, m equal to 4, b equal to 25, 25 into 4 is 100 micro 10 to the power minus 6, which is equal to 10 to the power minus 4 joule. So, the answer should be B. A paramagnetic substance of susceptibility 3 into 10 to the power minus 4 is placed in a magnetic field of 4 into 10 to the power minus 4 ampere per meter, then the intensity of magnetization in the units of ampere per meter is. Here susceptibility given, magnetic field given, you have to calculate intensity of magnetization. Magnetic susceptibility is nothing but magnetization divided by magnetizing field. So, M equal to chi multiplied by H. Chi is 3 into 10 to the power minus 4, H is nothing but 4 into 10 to the power minus 4, which is 12 into 10 to the power minus 8. So, the answer should be C. Needles N1, N2 and N3 are made of a ferromagnetic, paramagnetic and diamagnetic substance respectively. A magnet when brought close to them will be. Whenever a magnet is brought close to the ferromagnetic material, it gets magnetized strongly. Para, it gets attracted towards the para weakly. Dia, it is repelled by the diamagnetic material. Ferro attracts strongly, para weakly, but diamagnetic repels it weakly. Therefore, the answer should be N1 ferromagnetic attracts strongly, N2 paramagnetic attracts weakly, and N3 diamagnetic should repel it weakly. So, the answer should be N1 strongly, N2 weakly and N3 repels weakly. So, B is the answer. Rate of change of torque with the deflection theta is maximum for a magnet suspended freely in a uniform magnetic field of induction B when. So, rate of change of torque with the deflection theta should be maximum. You have to calculate the value of theta. Torque is given by mb into sin theta. Rate of change of torque d tau by d theta, nothing but mb into cos theta. This is maximum whenever cos theta is maximum. Cos theta is maximum when theta is 0 degree. So, when theta 0 degree, d tau by d theta is maximum. So, the answer should be A. The coercivity of a small magnet where the ferromagnetic gets demagnetized is 3 into 10 to the power 3. The current required to be passed in a solenoid of length 10 centimeter and number of turns 100. So, that magnet gets demagnetized when inside the solenoid is. Whenever magnet is placed inside the solenoid, it gets magnetized due to the field H. H is given by H equal to N into I. You have to calculate current required, I equal to H divided by N. H is given 3 into 10 to the power 3. N is number of turns per unit length, number of turns is 100, unit length, length is 10 centimeter, which is nothing but 0.1. 100 by 0.1 is 1000, goes with 10 to the power 3. So, the answer is 3 ampere. So, D is the answer. If the magnetic dipole moment of an atom of diamagnetic material, paramagnetic material and ferromagnetic material are denoted by mu d, mu p, mu f respectively, then in case of diamagnetic material there is no permanent magnetic dipoles, the magnetic dipole moment is 0. In case of para and ferromagnetic material, magnetic dipoles exist. So, dipole moment is non-zero. So, mu d is always 0, mu p and mu f are non-zero. So, the answer should be mu d 0, mu p non-zero. A is the answer. A bar magnet of length L and magnetic dipole moment M is bent in the form of an arc as shown in the figure. The new magnetic dipole moment will be. There is a bar magnet of a length L whose magnetic dipole moment is m, which is equal to qm into l. Now it is bent to form a arc at the center. It subtends an angle 60 degree. If you join the two poles, this is nothing but new distance L dash. Since this is 60 degree, this should be a equilateral triangle. All the sides are equal. L dash is nothing but R. So you have to calculate new magnetic dipole moment M dash, nothing but qm into L dash equal to R, which is equal to qm into R can be written in terms of arc. If I take this as S equal to L, arc length equal to R into theta, S equal to R into theta, therefore R is S divided by theta, which is qm into S is equal to L, theta 60 degree, which is pi divided by 3, which is equal to 3 qm into L divided by pi. Qm into L is nothing but m, which is equal to 3m divided by pi. So the answer is E. A bar magnet having a magnetic moment of 2 into 10 to the power 4 joule per Tesla is free to rotate in a horizontal plane. A horizontal magnetic field 6 into 10 to the power minus 4 Tesla exists in the space. The work done in taking the magnet slowly from a direction parallel to the field to a direction 60 degree to the field. So your work done to rotate the magnet is required. Initially it is parallel to the field, means angle theta 1 is 0 degree, then you have to turn it to angle 60 degree. Work done is given by the formula mb into cos theta 1 minus cos theta 2, which is m is given 2 into 10 to the power 4, b is given 6 into 10 to the power minus 4, theta 0 degree, theta 2 cos 60 degree. Cos 0 is 1, cos 60 is 1 by 2, 1 minus 1 by 2 is 1 by 2, 2 cancels, remaining is 6. So the answer should be 6 joule. So B is the answer. A dip needle lies initially in the magnetic meridian when it shows an angle of dip Q at a place. The dip circle is rotated through an angle x in the horizontal plane and then it shows an angle of dip q phi, then tan q divided by tan phi s. Whenever dip circle is in the magnetic meridian, it shows a actual dip or true dip, which is given by tan q equal to Ze divided by He. Whenever it is rotated through an angle x, this is the magnetic meridian, this is the new plane, angle equal to x. In this plane horizontal component is He, here it is nothing but He dash. Dip is tan q phi, which is same vertical component, different horizontal component, which is Ze by horizontal component is He cos x, which is tan q divided by cos x. You have to calculate tan q by tan q phi, which is equal to cos x. So the answer is D. The length of a magnet is large compared to its width and breadth. The time period of its oscillation in a vibration magnetometer is 2 seconds. The magnet is cut along its length into 3 equal parts and 3 parts are then placed on each other with their like poles together. the time period of this combination will be, there is a magnet whose length equal to L, time period is 2 pi root of I divided by mb. I is called moment of inertia, m is the magnetic dipole moment. Now it is cut into 3 equal parts along the length. Cut into 3 equal parts. Length of each becomes L divided by 3. No change in the pole strength. Therefore, new moment of inertia I dash is, whenever these 3 are combined now, all the 3 parts are combined, length equal to L by 3, mass remains the same. So, mass remains the same, length becomes L by 3 square by 12. Moment of inertia of the rod is given by ml square by 12. So, mass into length is L by 3 square by 12 equal to ml square by 12 is original moment of inertia, 3 square is 9. So, I dash is I by 9. There is no change in the magnetic dipole moment m, B remains the same. So, T dash by T equal to m same, B same, 2 pi same, only variable is I, root of I dash by I, which is root of I by 9 by I, which is 1 by 3, implies T dash equal to T by 3, T equal to 2 by 3 seconds. So, the answer should be B. Time period of a freely suspended magnet does not depend upon. Time period of a freely suspended magnet is given by 2 pi into root of I divided by m into B. It depends on magnetic dipole moment, means pole strength, depends on magnetic field in the region, moment of inertia depends on length of the magnet. Therefore, A, B, C are true, but it is independent of length of the suspension thread. So, the answer is D. Time periods of vibration of 2 bar magnets in some and difference positions are 4 second and 6 second respectively. The ratio of their magnetic moments is, whenever 2 magnets are placed such that they have magnetic moment in the same direction, then it is called sum position. They are placed such that magnetic dipole moment are in the opposite direction, then they are said to be in difference positions. Here time period T1 is 2 pi root of I by m becomes m1 plus m2 into B, T2 2 pi into root of I by difference is m1 minus m2 into T1 square by T2 square equal to m1 minus m2 by m1 plus m2. If you simplify, m1 by m2 equal to T1 square plus T2 square by T2 square minus T1 square. In some position, time period is 4 second, 4 square, in difference position 6 square, 6 square minus 4 square, which comes equal to 2.6. So, the answer is 2.6 is to 1 C. A coil of 1 turn is made of a wire of certain length, and then from the same length of a coil of 2 turns is made. If the same current is passed in both the cases, then the ratio of the magnetic induction at their centers will. There is a wire of length L. In first case, it is converted into a coil of 1 turn, second case it is converted into a coil of 2 turns. Field at the center of the coil is given by mu naught n into I divided by 2 times R. Mu naught constant, 2 constant, same current is flowing, n and R depends on number of turns. So, B proportional to n by R. Therefore, B dash by B equal to n dash by n into R by R dash. Initial number of turns is n, then it is converted into coil having 2 turns. Initial radius is R. Whenever number of turns doubles, radius becomes half, which is equal to 4. So, B by B dash is 1 by 4. So, the answer is 1:4. B is the answer. A cell is connected between 2 points of a uniformly thick circular conductor, and I1 and I2 are the currents flowing in 2 parts of the circular conductor of radius A. The magnetic field at the center of the loop will be. There is a circular loop. One terminal is connected here, another is connected to the some other part. It has to send current I, which splits into I1 and I2. O is the center. You can consider this as the 2 arcs. Since current directions opposite, should produce magnetic field in the opposite direction. Here current is flowing in this direction, produces field outward. Here field should be outward, here field should be inward. So, resultant field is nothing but B1 minus B2. Apply Biot-Savart's law. According to that, field is mu naught by 4 pi into ideal sin theta by r square. Both have same radius, both have same angle theta. So, field depends only on current into length. If length is more, resistance is more, current is less. If length doubles, current becomes half. Therefore, I into L is constant here. I into L is constant, implies B1 comes equal to B2, implies net field equal to 0. So, the answer is E. A proton carrying 1 mega electron volt kinetic energy is moving in a circular path of radius r in uniform magnetic field. What should be the energy of a alpha particle to describe a circle of same radius in the same field? So, both charged particles are moving in the same field, should describe the same circular path of same radius. You have to calculate energy of the alpha particle. Radius of the path in terms of energies, root of 2m into kinetic energy divided by q into b. Here r is same, b is also same, but m is different, mass is different, charge is different, kinetic energy is also different. So, one is proton, second is the alpha particle. So, r into qb root of 2m into ek. Therefore, r constant, b constant, root of m ek divided by q equal to constant, ek equal to q square by m. Therefore, energy of alpha by energy of proton is q alpha by q proton square into m proton by m alpha, which is equal to charge of alpha is twice the proton, mass of alpha is 4 times the proton. 2 square 4 goes with 4, 1 implies E alpha equal to EP. So, the answer should be 1 MeV. B is the answer. An electron beam is shot into a region containing electric field of 10 Newton per Coulomb and magnetic field of 2 Tesla. If the electron beam passes undeviated, then velocity of electron beam in meter per second is. If a charged particle enters a region containing both electric and magnetic fields, it goes undeviated only when its velocity v equal to E divided by B. So, E is given 10 Newton per Coulomb, B is given 2 Tesla, 10 by 2 is nothing but 5. So, velocity should be 5 meter per second. So, the answer is A. An electron moving with a velocity of 10 to the power 6 meter per second enters a magnetic field first at an angle of 90 degree and then at an angle of 45 degree to the field. The forces acting on the electron in two cases are in the ratio. A charged particle enters the same field with the same velocity but with different angle theta. You have to calculate ratio of the forces acting in the two cases. Force acting on the charged particle is QVB into sin theta. Here these three, so F proportional to sin theta. So, F1 by F2 equal to sin theta 1 by sin theta 2. Theta 1 is 90 degree, theta 2 is 45 degree, 1 by root 2 is nothing but root 2. So, the answer is root 2 is to 1 A. A current of 1 ampere is passing in the sides of equilateral triangle of side 4.5 10 to the minus 2 meter. The magnetic field at the centroid is. A equilateral triangle is given, all the three sides are equal which carry current I. Find out magnetic field at the center. So, currents are in this direction, field is outwards, outwards, outward according to right hand clasp rule. So, all the three conductors are at same distance from the point, produce a same field. Therefore, total field is nothing but 3 times the field due to one conductor. If I take this conductor AB, join the edges to the center. This is the distance R. If I take this as alpha, this should be beta. Both alpha and beta equal to 60. This is 60, 30, 90 implies this should be equal to 60 degree. If side equal to A, this is equal to A by 2. Therefore, this is 3 times. Field is given by the formula mu naught I by 4 pi R into sin alpha plus sin beta, which is 3 into mu naught by 4 pi is 10 to the power minus 7 into I by R is nothing but define tan alpha, opposite side divided by adjacent. Therefore, adjacent is opposite by tan alpha, which is A by 2 divided by tan alpha into sin alpha plus sin beta, which is equal to 3 into 10 to the power minus 7 into current equal to 1 ampere. A by 2 4.5 into 10 to the power minus 2 is the side by 2, alpha and alpha goes to numerator, tan alpha 60 degree, sin 60 degree, sin beta 60 degree. What is the relation between voltage sensitivity and current sensitivity of moving coil galvanometer, where G is galvanometer resistance? Current sensitivity SI is nothing but deflection divided by current. Current required for unit deflection is called current sensitivity. Voltage sensitivity is nothing but potential difference required for unit deflection theta by V. This can be written as theta by V is current into resistance, but theta by I is SI. So, SI by G is nothing but SV. So, the answer should be sigma V or SI. B is the answer. The time period of a freely suspended magnet is 4 seconds. If it is broken in length into 2 equal parts and one part is suspended in the same way, then its time period will be a magnet of length L is oscillating, time period is 2 pi root of I divided by mb, which is equal to 4 seconds. Now, this rod is cut into 2 equal parts, length of one becomes L divided by 2. Mass of total is m is one part becomes m divided by 2. Therefore, moment of inertia is mass into length square L by 2 whole square divided by 12, which becomes ml square by 12 is original moment of inertia, 1 by 4 into 1 by 2 is 1 by 8. So, I divided by 8. Therefore, new time period is T dash by T root of I dash by I into m divided by m dash, which is equal to root of I dash by I is nothing but 1 by 8, original magnetic moment m. Now, length becomes of, therefore, magnetic moment becomes of m by 2, which gives rise to 2 by 8, 1 by 4, 1 by 4 root is 1 by 2. Therefore, T dash is T by 2, 4 by 2 equal to 2 seconds. So, the answer is B. A magnetic dipole is under the effect of two magnetic fields inclined at 75 degree to each other. One of the fields has a magnitude of 1.5 into 10 to the power minus 2 Tesla. The magnets come to stable position at an angle of 30 degree with the direction of the above field. The magnitude of the other field is, here magnetic dipole is under the effect of two fields inclined at an angle of 75 degree. One field is B1, another field is B2, angle between the two is 75 degree. Now, the magnet comes to equilibrium by making an angle of 30 degree with one, implies with the another it should make an angle of 75 minus 30, nothing but 45 degree. The magnitude of the other field is required. So, for equilibrium net torque should be 0, implies tau 1 equal to tau 2, which is m b1 sin theta 1 should be equal to m b2 sin theta 2, same magnet, m constant. So, you have to calculate the value of other field b2 equal to b1 sin theta 1 by sin theta 2, b1 given 1.5 into 10 to the power minus 2 sin theta 1 30 degree sin theta 2 45 degree, which is 1.5 into 10 to the power minus 2 sin 30 1 by 2, 45 degrees 1 by root, which is equal to 1.5 into 10 to the power minus 2 by root. So, answer should be B. Two identical short bar magnets, each having magnetic moment of 10 ampere meter square, are arranged such that their axial lines are perpendicular to each other and their centers be along the same straight line in a horizontal plane. If the distance between their centers is 0.2 meter, the resultant magnetic induction at a point midway between them. So, here two identical bar magnets given such that axes are perpendicular to each other. If this is one magnet, this is the another magnet, axes are perpendicular to each other, center of one is O, another is O dash, that two are separated by a distance of 0.2 meter. You have to calculate magnetic field at a point P at a distance of d, which is 0.1 from 1 meter from each of them. For one magnet it is the axial point, for another magnet it is the equatorial point. Therefore, this produces if I take this as minus q plus q, should produce field in this direction. This produces magnetic field perpendicular to that, implies two fields are perpendicular to each other. Therefore, net field is root of B1 square plus B2 square. For one it is the axial point, another it is the equatorial point. Therefore, if I take B1 axial point, mu naught by 4 pi into 2m divided by d cube whole square plus for another mu naught by 4 pi into m by d cube whole square, which becomes root 5 times mu naught by 4 pi into m divided by d cube, which is equal to root 5 into mu naught by 4 pi is 10 to the power minus 7. Magnetic moment is 10, distance is 0.1, which is 1 into 10 to the power minus 1 cube, which is equal to 10 to the power minus 3 becomes plus 3 plus 1 plus 4 plus 4 minus 7 minus 3. So, the answer is root 3 into 10 to the power minus 3 Tesla. So, answer is D. The angle of dip at a place is delta if the dip is measured in a plane making an angle theta with the magnetic meridian. The apparent angle of dip will be, the angle of dip at a place is delta, which is the true dip. If the dip is measured in some other plane which makes an angle of theta with the magnetic meridian, we get apparent dip. You have to calculate the value of apparent dip. So, in the magnetic meridian there is horizontal component HE. If I consider some other plane, in that horizontal component is HE dash. Angle between the two is nothing but theta. For both of them, vertical component is the same. Therefore, tan delta, delta is the true dip, is ZE divided by HE. Tan delta dash is the apparent dip, which is ZE by HE dash, which is ZE divided by HE cos theta, implies tan delta dash equal to tan delta divided by cos theta, or delta dash is tan inverse of tan delta 1 by cos theta is secant theta. So, answer is tan inverse of tan delta into secant theta. So, C is the answer. Two identical magnetic dipoles of magnetic moments 1 ampere meter square each placed at a separation of 2 meter with their axes perpendicular to each other. The resultant magnetic field at a point midway between the dipoles is. Two identical dipoles are given such that their axes are perpendicular to each other. Distance between their centers is given, which is nothing but 2 meter. You have to find out a field at a distance 1 meter from each, midway between the two. For one it is the axial point, another it is the equatorial point. So, definitely two fields are perpendicular to each other. So, net field should be root of B1 square plus B2 square, which is root of mu naught by 4 pi into, if I take first one axial point, 2m by d cube. For another equatorial point, which is m by d cube whole square, which gives rise to root 5 into mu naught by 4 pi into m by dq. Root 5 mu naught by 4 pi is 10 to the power minus 7. Dipole moment is 1, distance is 1 meter. So, which is equal to root 5 into 10 to the power minus 7. So, the answer is B. A bar magnet of length 6 centimeter has a magnetic moment of 4 joule per Tesla. Find the strength of magnetic field at a distance of 200 centimeter from the center of the magnet along its equatorial line. There is a bar magnet here, length is given 6 centimeter. Now, there is a point at a distance of 200 centimeter along the equatorial line. Field is given by the formula mu naught by 4 pi into m divided by dq, which is mu naught by 4 pi is 10 to the power minus 7. Dipole moment is given 4, distance given 200 centimeter is nothing but 2 meter 2 cube, which is nothing but 2 cube is 8, 4 by 8 is 1 by 2. So, 1 by 2 into 10 to the power minus 7, which is 0.5 into 10 to the power minus 7 or 5 into 10 to the power minus 8 Tesla. So, the answer is C.